For most of the chapter, we're going to cover a reaction called nucleophilic acyl substitution. So we're going to start by looking at the general reaction, the general mechanism for this reaction. So carboxylic acid derivatives have an acyl carbon that has some sort of leaving group, which we're going to abbreviate with the letter Y, that can be replaced by a nucleophile. This reaction has some similarities to nucleophilic addition reactions, which we covered earlier this semester. Nucleophilic addition reactions is a reaction that occurs with ketones and aldehydes, where a nucleophile adds to the carbonyl carbon. It breaks the double bond of the carbonyl to give us an alkoxide intermediate. So alkoxide means we have a negative charge on the oxygen. We sometimes refer to this intermediate as a tetrahedral intermediate. So it's tetrahedral at the center. At this point, for most nucleophilic addition reactions, this oxygen will react with aqueous acid to give us the final product, which has an alcohol and some sort of nucleophile added to the same carbon. So overall, this is a nucleophilic addition because we're adding a nucleophile to the carbonyl. Now, in this chapter, we're going to look at acyl substitutions, which involve typically an acid derivative. The difference between the acid derivatives and ketones and aldehyde is that the R group here, R prime specifically, is either an alkyl if it's a ketone or a hydrogen if it's an aldehyde. Both of those are very poor leaving groups. So when we get to the tetrahedral intermediate, there is nothing else to do for this intermediate other than getting rid of this negative charge by protonating the oxygen. However, when we get to a carboxylic acid derivative, this Y group differs a lot from an alkyl or a hydrogen. So typically, this Y group is a decent enough leaving group that when we get to the alkoxide intermediate, we can do an elimination instead. So the reaction starts the same way as nucleophilic addition reactions. So a nucleophile adds to the carbonyl, breaks the double bond to get to the alkoxide intermediate, or what we call the tetrahedral intermediate. Then this alkoxide intermediate will reform the carbonyl by eliminating whatever the leaving group is on the acid derivative. And therefore, as a result, this reaction is a substitution reaction where the nucleophile is replacing whatever the leaving group is on the acid derivative. Let's take a look now at the differences in reactivity between different acid derivatives and also compare them to aldehydes and ketones. So in general, amides are the least reactive acid derivative towards nucleophiles. Esters are next, so they are quite unreactive compared to other acid derivatives, but not as much as amides. Acid anhydrides are even more reactive. Acid chlorides are even more so. Now, if you're wondering, acid bromides are even more reactive. Now, we're not going to see too many examples because acid bromides are so reactive that they're sometimes very difficult to work with. Carboxylic acids, if you're wondering, depends on the reaction, but they're somewhere between an ester and an amide. So sometimes they're put around where the ester is. Sometimes they're put a little bit less reactive. It kind of depends on the reaction conditions. Aldehydes and ketones, as we just learned, they don't undergo acyl substitutions. So with nucleophiles, they do an addition reaction instead. But as far as reactivity towards nucleophiles, aldehydes and ketones are somewhere in here. They're not as reactive as an acid anhydride, but they're less reactive than esters. And between aldehydes and ketones, aldehydes are generally more reactive than ketones. Now, the trend that we observe on this chart here is due primarily to how good of a leaving group we have. So generally, the acid, bromide, and chloride have really great leaving groups. Then hydrides have a pretty decent leaving group. Esters, they don't have as good of a leaving group. And amides have the worst leaving group from the acid derivatives shown here. The leaving groups, how good of a leaving group it is, depends on a few factors. For example, the electronegativity of the atoms that is attached to the carbonyl. It has to do also with the resonance stabilization of a negative charge. So in the case of anhydride, the leaving group is this essentially a carboxylate group, which has a negative charge on this oxygen once it's kicked out, which can be resonance stabilized. So for that reason, anhydrides are a little bit better. They have a better leaving group than the esters. The chlorides and the bromides, they have halogens, which they don't bond or they don't form a very strong bond to carbon because the orbitals of chlorine and bromine are slightly different sizes than the orbitals on carbon, so they don't overlap very well, and so they tend to form a very weak bond. Chlorine and bromine also are fairly electronegative, so they make for great leaving groups. And there's a few other reasons. Sometimes we use the explanation that the nitrogen, for example, can resonance stabilize into this carbonyl, so it makes that bond really strong. There are many reasons we sort of explain the trend we see here. The acid derivatives can be interchanged between so from one acid derivative to another fairly easily. It is even easier when you start off with a more reactive acid derivative in converting it to a more or a less reactive one is a lot easier to do. So if we start off with an acid chloride, it's a lot easier to convert it into an anhydride, and the rest of the other acid derivatives is a lot harder to go from an amide to the rest. Although some reactions are possible to go the other way around. But in general, it's a lot easier to go from the anhydrides and the chlorides to the other acid derivatives rather than the other way around. There are other factors that will influence the reactivity of a particular carbonyl compound. For example, using an acid, whether it's a Bronsted or a Lewis acid, will help to quote unquote activate the carbonyl and make it more electrophilic and therefore more reactive towards nucleophiles. So if you have one of the acid derivatives like an amide or an ester, which are generally considered less reactive, we can still get them to react if we activate the carbonyl first by using a Lewis acid or a Bronsted acid. So in general, a Lewis acid or Bronsted acid will bond to the carbonyl oxygen and form an intermediate like this that has a positive charge on the on the oxygen. That makes this carbon of the carbonyl more electrophilic than without that activation, that bond to the Bronsted or the Lewis acid. Sterics also plays a role in the reactivity of different carbonyl or acid derivatives. So if we have several alkyl groups that are fairly bulky near the carbonyl, that will make the carbonyl carbon less reactive towards nucleophiles. So having several hydrogens in this alpha carbon means this carbonyl is more reactive towards nucleophiles than having several alkyl groups on that same alpha carbon.